I'm going to give you a status update, a quick status update on Xenon ARM. And I'm going to also show some benchmark results to compare Xenon ARM to Xenon x86, as well as KVM on ARM and KVM on x86. So status. So Xen 4.4 was released in March this year, featuring a 64-bit stable, 64-bit guest support, stable hypercall ABI, so that's maintained for backward compatibility going forward. Supporting all the basic lifecycle operations, so we can create VMs, destroy VMs, rebooting VMs, pausing VMs, all the basics. Memory ballooning, so increasing and decreasing the memory reservation of VMs at runtime. Scheduler configuration, vCPU pinning, and CPU pools. So as you know, we have different schedules in Xen. They are all supported on Xenon ARM. We can pin virtual CPU to physical CPUs. We can split physical CPUs into different CPU pools and run different schedulers in different CPU pools. In terms of platforms, we support the ARMv8 FVP, that is an emulator, 64-bit emulator by ARM. The Arndale board, all Windows NXide, the really cheap dev board. O'Neill used it. I would recommend this one if you want to try to hack on Xenon ARM. TI OMA 5 and Apply Micro Xen, that is a 64-bit SoC, ARMv8 SoC. Linux 3.13 similarly was released at the beginning of the year. It support booting on Xen as DOM0 or as DOMU, 32-bit or 64-bit. SMP, so support for multiple vCPUs. Software relative big Xen is a complex driver that allow you to store the guest disk image on a physical partition or on an LVN volume. And all the PV drivers in Linux are supported. So disk, network, console, frame buffer, keyboard and mouse, both front-end and back-end. So all of this is basically all news, is what the status was at the beginning of the year. Now we are much farther ahead. So this is a feature list for 4.5 regarding Xenon ARM. So as you can see, it's a really long list, considering that we developed all these features just in the last 6 months. So it's actually quite impressive. So if we look at the status of the features, the green ones are the ones that are either already committed to the tree or they are about to be committed. So it's a long list. The yellow ones are the ones that are still in development. They might make it or they might not. So yeah, overall you might have noticed that the traffic on the mailing list has increased. So in fact, in the last 4 months, the traffic is up almost 20% compared to the previous 4 months. If we look at a year period, the traffic is up like 35% compared to the previous year. So if you're complaining that it's difficult to catch up on xen-devel lately, think of the poor maintainer that need to review all this code, right? So they might feel a bit overloaded, right? Yeah, I would like to take the opportunity, to yeah, so please help review the code. If you have some time, especially patches that touch, that modify the code you contributed in the first place, or even if you just have time to review 1 patch a day, it will still be helpful. Now, I'll try to spend a few words on all these features, but there are lots. So I'll try to divide them in categories. The first category is performance improvement. And the first feature, RQ latency reduction, no maintenance interrupts. So before, so in 4.4, what we used to do, this is just an example. So RQ 109, interrupt 109 would interrupt the physical CPU. We will get into Xen. The hypervisor will receive the interrupt and write to the GKHLR register to inject the corresponding virtual interrupt into the virtual CPU. So virtual interrupt, virtual RQ 109 will be injected in the guest, DOM0, for example. DOM0 will handle the interrupt, and at the end, it will EOI the interrupt. EOIing the interrupt from DOM0 causes a second interrupt to occur. This second interrupt is called maintenance interrupt, and it was used by Xen to clear the status of the registers. So getting rid of the maintenance interrupts is simply means getting rid of the second interrupts. That means receiving only 1 physical interrupt for each physical interrupt rather than 2, like we did before. And this is why it's a performance improvement. The second one is support for interrupt priorities. So the GeekV2 spec introduces the concept of interrupt priorities for group of interrupts. So a higher priority interrupt can interrupt a lower priority interrupt. We didn't support this in 4.4. We now do. Linux does not make use of interrupt priorities, but other OSs do. So for example, FreeRTOS uses interrupt priorities, and now it runs OK on Xenon ARM. RQ migration. So you might know this feature also as RQ balancing. So let's suppose, again, it's like in the same example as before, interrupt 109 interrupts physical CPU 0, and then Xen injects the corresponding virtual interrupt 109 into virtual CPU 0. That, for simplicity, is running on physical CPU 0 here. Now, what if the guest want to move the virtual interrupt 109 is receiving on vCPU 0 to vCPU 1. This is what will happen if you have a lot of interrupts on vCPU 0 and you enable the RQ balancing daemon. Not only, so first of all, this was not supported in 4.4. Second of all, it's not sufficient to just move the virtual interrupt 109 delivery from vCPU 0 to vCPU 1, because then it gets really slow. You keep getting the physical interrupt on the wrong CPUs, and you have to send IPIs and so on. So what this work is about is when the guest asks to move virtual RQ 109 from vCPU 0 to vCPU 1, we also move the corresponding physical interrupt from physical CPU 0 to physical CPU 1, so that you always receive only the minimal amount of interruption. Another complex feature is multi-ground support. So this is a cross between a bug fix and a feature, and a performance improvement, to be honest. So the problem is that sometimes the front-end driver, right, will share the same page multiple times using multiple grant operation. So what happens is the backend driver will map all these pages without even knowing that it's the same page. So the same page will end up mapped in DOM0 at multiple different guest physical addresses. So, and all these pages obviously would have a different PFN in DOM0, but the same MFN. So what's the problem with having the same MFN? The problem is the Linux DMA API at some point give you, in DOM0, give you a DMA address that is an MFN, and you need to do an operation on it. So how do you get the right page to do operation on if there are multiple pages that correspond to this MFN? So this is a difficult problem to solve. You could try to access any of them, but then maybe because you access the wrong one, I know it's the same page, but it could be unmapped while you're working on it. So the way we solve the problem is we got rid of the MFN to PFN tracking in DOM0 that is very expensive. It's based on a red-black tree. This is why it's a performance improvement. So there is no MFN to PFN anymore. So what we do is Xen will map the page twice. We'll map the page wherever DOM0 wants the page, and it will also introduce an identity mapping. So it will map the page at PFN equal MFN. So DOM0 always know where to access this data because it's a MFN equal PFN address. And this solved the problem for multiple grants. So the problem on Xenon ARM specifically was introduced in Linux 3.15 when an improvement to net front, net back would cause suddenly net front to actually send multiple, to share the same page multiple times with multiple grants. So if you're running 3.15 without this bug fix, you actually can incur into trouble. So another really important performance improvement that was worked on by Ian Campbell is super page support. So now you can have 2 megabyte pages in the guest P2M that really speed up the guest access to memory. We do now support up to 1 terabyte of guest RAM, and we do support sparse memory map. So on platform where there are multiple banks of memory and they are mapped at very different physical addresses. We now support them on both Xen and DOM0. And we also support 48-bit physical addresses. So next category is new hardware and new firmware interfaces. So Julian Graal contributed the SMMU driver in Xen. The SMMU is the ARM version of an IOMMU. So now we can use that to do, it's going to be used to do device assignment and as well as to improve performance in DOM0. Because thanks to the SMMU, we will be able to avoid the software UTLB Xen driver that is a famous driver with all the tracking on MFN and PFN and is a bit slow. We want to support UEFI supporting Xen, we want to support UEFI booting in Xen. So Linaro is working on this. Patches have been sent, and they're mostly about moving UEFI support code from x86 specific directories into common code. PSCI, so PSCI is a firmware interface to start secondary CPUs as well as rebooting the system. And we support it at both the hardware level in Xen and at the virtual level, exposing this interface to virtual machines. And we upgraded the PSCI support in Xen in both levels to 0.2. Finally, probably the most important feature among these is GigV3. Because GigV3 is an update of the interrupt controller. Previous one was known as GigV2. And GigV3 not only is really different from GigV2, but it supports MSIs and removes the limitation of only 8 physical CPUs. This has been contributed by KVM Networks. In terms of brand new features, Julian also worked on device assignment on ARM. So now you can assign, for example, a network card on an Lambda bus to a guest, non-PCI for the moment. QEMU PV backends. So as you should know, QEMU is not just a machine emulator. It's also a provider of Xen paravirtualized backends in user space. It provides a frame buffer, a mouse, a keyboard, and a console backend. So we want, at the very least, the frame buffer, mouse, and keyboard backends are useful. So now we can build and run QEMU on ARM to provide this backend. So we still do no emulation whatsoever on Xenon ARM. MiniOS on ARM. So MiniOS is a tiny BSD kernel that is a unikernel. It's used to run a single application in kernel space, and it's been ported to ARM. What's missing from this long list? Save, restore, and line migration. So we thought we will get actually line migration and save, restore in 4.5, but we won't. So the contributors went away. So we will have to look at this feature for 4.6. PCI device assignment, we just didn't get to it yet. It's on our roadmap. People are working on it, but it certainly won't make it for 4.5. The other 4 work items are things I know people are working on, and I might have even seen patches, but they're not going to make 4.5. So IOMMU emulation for remote processor. This is a bit complex. So let's suppose you have a platform with 1 or more accelerators, like a crypto engine. And let's call this accelerator remote processors. Now you want to assign these remote processors to the guest. However, they're not protected by an IOMMU. So you need to remap, obviously, the MMIO region and the RQs to the guest, but that's not sufficient. You also need to trap the command stream and translate the guest physical addresses into physical addresses. And this is exactly what this work does. And that's been contributed by Global Logic. GigV2M support. This is an update of the GigV2 interrupt controller with MSI support. SMMU V2 is an update on the SMMU. It contains actually lots of new features, but from Xen point of view, it's basically the same as SMMU V1. So it should be really easy to make it work. And finally, SCPI support. People in Linaro are working on getting Xen booting on an ACPI systems, and I have even seen demos of Xen booting on ACPI, but it's still a work in progress. Yeah, before moving to the benchmarks, I would like to spend a few words on the embedded and automotive initiative. So the Xen project, as you might have read, is kicking off a new initiative for embedded and automotive scenarios, to create a focal point of collaboration within the Xen community for example, to write para-virtualized drivers for embedded and automotive scenarios. So for example, PV drivers for the compass, the GPS, or audio, or 3D graphics, as well as maintaining ports of embedded OSs such as QNX. Global Logic is going to contribute the first few set of PV drivers a port of QNX and a port of Android to Xenon ARM. Especially for the one of you that were present at Xen Developer Summit 2013, we spoke exactly about this. And we tried to find a way to collaborate on embedded and automotive, and this is exactly it. Right, the interesting part, benchmarks. So given that the project is not that new anymore, what I wanted to do is to validate the project, to find out how fast does it go, and to see whether we did anything wrong. This is the first set of benchmark I ran, so maybe there is a bottleneck or something that needs to be fixed, just to see how well we are doing, really, how healthy is the project. So to do that, I use Linux 3.15 RC8. I use it as DOM0, DOM-U, and native kernel. I use Xen 4.5 as of July, plus a couple of patches to disable the debug build and a few debug traps. QEMU KVM 2.0 for the KVM tests. OpenSUSE 13.1 as DOM0 and as DOM-U, and also for the native execution. So the idea here is I wanted to run a benchmark in a VM and a benchmark on native and see how much slower is running the benchmark in the VM. So to do that, I run native Linux on both an Applied Micro Xgen and V8 SoC with 8 cores, and an Intel Xeon Westmere CPU. 2 sockets, but I disabled, it's a bit old, I admit it, that's the reason is the most common test machine in our environment. So it's the one I usually use for x86, so I didn't set up a new system, I admit it. It has 2 sockets, to avoid any NUMA issues or any bad NUMA interaction, I disabled one of the 2 sockets. So I'm only using one of the 2 CPUs with 6 cores. So the idea is I run Linux on both platforms natively, reducing the RAM, the amount of RAM available to Linux only to 2 GB. And then I rebooted and ran Xen, and then started a VM, giving only 2 GB of RAM to the VM, and the same number of virtual CPU as of physical CPUs on the system. So in the case of the Applied Micro Xgen SoC, I will give 8 vCPUs to the VM and still 2 GB of RAM. Comparing the results, I'm showing the results in terms of overhead. So lower is better. So 0 means running the benchmarks inside the VM is just as fast as native, and it's in percentage. So as you can see here, Kernbench is a time to compile the Linux kernel, and Xenon ARM is close to 0 overhead. Xenon x86 is second best and is 2%, around 2% of overhead. KVM on ARM is about 3%, and KVM on x86 is about 7%. So I'm really happy with this. This was the first result I got, and it's a good validation point. So Xen, it has a lower overhead than KVM in general, and Xenon ARM tend to be particularly well here. The second benchmark I run is PBzip2. That is a parallel implementation of bzip2, and it's compressing, software. So I measured the time to compress a 4 GB movie in bzip2. Again, Xenon ARM is about 1% of overhead. Xenon x86 is 3. KVM on ARM is 4. KVM on x86 is 9. So it's about the same picture that we got from before. The next one is FIO. FIO is a popular disk benchmarking suite. Here, I run random read-write benchmark. Again, lower is better, means closer to native performance. Xenon ARM is about 1%. Xenon x86 is basically a 0 overhead. KVM on ARM 8, and KVM on x86 is about 2. So here, the big loser in this benchmark is KVM on ARM. So I believe, so you will see later also from another benchmark, I believe the VirtIO disk might have an issue with the KVM version I used, because I did enable everything I could in terms of vhost, in terms of transparent use pages, everything. But 8% is quite a bit. It's quite a bit of overhead for a simple disk benchmark. And there is another benchmark later that involves disk I/O that is also suffering. Okay, this is probably the most surprising result I had. SpecJBB 2005 is the Spec Java server workload benchmark. So Xenon ARM has a lower overhead than KVM on ARM, and Xenon x86 has a lower overhead than KVM on x86, but the difference between ARM and x86 is quite big. And it's bigger than I expected. So I ran this test several times, and to try to understand why, because it shouldn't be, I didn't expect to be this high. So one thing I found is that there is a performance regression on x86 between 313 and 315 RC8. To give you an idea, this test on 313 would be here for Xenon ARM. Xenon x86 would be about 3%. And KVM on x86 should be about 7. So something made the performance on both KVM and Xenon x86 between 313 and 315 RC8 slower, and I don't know exactly what. Another thing to keep in mind is that SpecJBB and Java in absolute number is much faster on x86 than on ARM, because Java is far more optimized on x86. So this also might affect the overhead. Finally, I did find out that transparent use pages, they do make the numbers better for both the virtual and the native execution, but they make the numbers better for the native execution proportionally. So enabling transparent use pages will make the overhead higher. Everything goes faster, but the native goes much faster than, about 1% faster than the virtualized execution. So overall, this is a bit strange, but yeah, these are the conclusion or the analysis I managed to do on this benchmark. PGBench, this is a Postgres benchmark, database benchmark. Xenon x86 and KVM on x86 are basically both 0 overhead here. Xenon ARM is about 1 or 2%, so it's doing all right. Again, KVM on ARM is not doing all right. So you might have noticed here that it's 20%, but that's just because it's how big the picture I could fit in this slide. So really, the overhead here is 120%. I ran the test several times. Yeah, there must be a bug in the version I used because this level of overhead cannot be called anything else. But yeah. So yeah, one last benchmark I wanted to show is a benchmark that has been contributed by Apply Micro, the maker of the Xen SoC, and is SpecINT. It's a popular integer crunching numbers set of benchmarks. So the interesting bit is they actually used a quite different deployment scenario. So what they've done is they random 0 with 1 vCPU and 7 guests, each of them with 1 vCPU. It's an 8-core system after all. And they run SpecINT in parallel on the 7 guests. And they aggregate the numbers. Then they run the SpecINT on native with all the resources and compare the results. It is very different from what I've done, but still the overhead, it's quite low, and it's about 2%, so it's a very good result. So I don't have the Xenon x86 or KVM on ARM, KVM on x86 number on this benchmark. So conclusions. Something went wrong there, obviously. Oh well. So we have many new features coming in 4.5. Good performance results, especially for a project that just came out of tech preview. And still we have a lot of room for improvements. So in terms of things that I would like to see, but probably I won't get, is more reviewers. So please help review the code. And as you know, Lars was saying in his talk yesterday, we're starting to see some sort of bottleneck on the reviewer side. So yeah, any help here would be appreciated. And that's it. Do you have any questions?
Could you talk about ARM across different manufacturers and how, I mean, what the story is there? Kind of give us some color.
So in what space? Server space, embedded space, anything?
Well, you have this code, so, and you listed a few different docs, but there's many more manufacturers than that. So are we moving towards a point where we're going to get the vast majority of our manufacturers will,
so
this code base will work for them, et cetera?
Yeah, of course.
And what are the
right.
problems you might have encountered with different vendors?
Right. So one of the problems with the ARM ecosystem is much more variegated and different compared to the x86 world. However, on the server side, they're trying to standardize on few core technologies such as UEFI and the CPI, so that in theory you will need only a single build and run on all the servers, similar to what you do today on x86. Basically, there is no ARM server today on the market that you can actually go and buy that has all these features, so that you can, in theory, come with your ISO and install your system. But you should be able to see them in the next few years, coming out soon. So on the embedded systems, they're likely to stay very different from one another. But porting Xen from one to the other is actually quite simple, because Xen doesn't use much hardware, right? It uses CPU, timers, the interrupt controller, maybe with SMMU, but they're all really standard, and usually all the embedded manufacturer, or almost all, they use the ARM IP for this. So porting Xen is relatively simple.
People that use lots of ARMs, and I mean, there's just so weird stuff going on.
Yes.
A lot of the weird stuff is stuff that will be driven by the DOM0 kernel, though, not by Xen. So if you have a native kernel support for it, Xen is a relatively trivial set.
So what usually happens is that they sell this SoC, and they give you a Linux tree that is not even the upstream tree, it's their own port of Linux to their board. And then the only thing you need to do is to get Xen running on it, and usually it's like a week or two of work. And you just use the Linux tree from upstream. This is how we got the SunXI or the OMA 5 port, and it was just like contributors, not us doing them. So.
And on the Linux side, they're trying to integrate that all together. So
yes, on Linux side is a real issue, and the Linux maintainers are working hard to get an integrated, solution.
Can you explain why Xen is better than KVM? Why the overhead is less?
It's difficult. So it's easy to guess. So on ARM, the Xen architecture is a better fit for the ARM virtualization extension than KVM. So it's kind of easy to explain why Xen on ARM has a lower overhead than KVM on ARM. Some of the difference between the overhead on ARM and x86 in these benchmarks, the difference is probably due to the fact that the Westmere CPU is a bit old. So maybe on a newer CPU there will be less difference. So I think that the context switch between the guest and hypervisor, it's less expensive on ARM. And so this is why on CPU or memory benchmarks, you would see that I think ARM has a lower overhead. So Xenon ARM will have a lower overhead than Xenon x86. Xen and KVM on x86 is a more difficult guess for me to make. So maybe the PV protocols are actually a bit better than VirtualIO, or maybe just the hypervisor side of the hypervisor traps are implemented a bit better. So these are actually the memory and CPU benchmarks have very, very little I/O in them. So it's probably not anything related to I/O. So yeah, it's difficult to guess. Yeah. Any other question? No? Okay. Thank you.